To recap, in the last few streams, I have been working on a tool called the GB header extractor, and it was a tool to go through GameBoy ROM files that you have laying around somewhere in a folder, and it would extract all the header information out of there. What is stored in the header information? Well, things such as the game title, the version number, what kind of ROM is being used, how big the ROM is, even, so all this kind of information. Now, I think this information was largely intended to be internal for Nintendo. The Game Boy doesn't do anything specific with it, right? But nonetheless, you will find this information on every Game Boy cartridge that has been gone through the official registration process with Nintendo, because you simply need to provide that data. Other cartridges, such as bootleg ROMs, would not have this information attached to them, except for one specific thing, and that is the Game Boy logo. Right, so the Game Boy logo, if you remember, if you watch the past streams, is basically just a way of copyrighting ROMs. Nintendo would encode the logo that is appearing on the start of the Game Boy, when it scrolls down, into each and every ROM, and it does compare that data. All the Game Boy needs is basically the logo data within the header, and then the checksum of the header. Now the checksum is calculated with all the information that's stored in there, but a bootleg or homebrew ROM, it doesn't really need to care about those things, right? We can just add whatever checksum we want, and instead of encoding the game title and the version number or which cartridge is being used, we can just put game code in there. There's nothing stopping us from doing that, and I think some bootleg ROMs actually are doing that. And as far as I know, it doesn't even compare the whole logo, but just the first row of bytes due to a bug. But I need to confirm on that. I think it depends on the model number as well. So technically, you can only populate half of the logo and then use the rest for code as well, if you so choose. But anyways, so we wrote this little tool to extract all that data. I have not put it up on my website to download yet, which is still something that I definitely want to do. I will share the links in a future stream as well and everything. But now I kind of want to go one step further, right? The idea of me doing these streams is to basically learn how a CPU works on a very low level. Because that's something I've never had to deal with, right? And I also want to learn what it takes to build all that software that we as programmers use daily. What it takes to build this kind of software to be able to then write code for a specific system, right? And I didn't want to start with something very complicated like ARM processors or dive straight into x86, right? Even though I technically could do that, the documentation is all there, but there's so many layers involved that remove you from the system. Even if you go to a Raspberry Pi, there's lots of additional layers involved that just make it really complicated to distract from what I'm trying to learn. So the best thing I thought would be to just, the Game Boy. It is a very straightforward machine. All it's doing is it's playing data from the cartridge. It has very simple inputs defined. It has graphics capabilities. It has sound capabilities. And if you so choose, it even has networking capabilities, right? Although, it technically can be network, right? But whatever you can put in here, you can basically talk to other devices if you want to. You just need to follow the protocol. Whatever happens on the other device or whatever the other device is, doesn't really matter. Same for the ROM, actually. If you remember, there's the Game Boy camera and stuff like that. So you could actually do a lot with this little device. In fact, there was one prototype which kind of went into obscurity, which is a whole what do you call it? Basically, basically they're trying to make the Game Boy as a home computer. So it would have a keyboard, it would have some storage attached to it and stuff like that. Let me see if I can find a screenshot actually. And for that, we're gonna go to my machine. Hang on a second. There we go. I think it was called the Working Boy. Working Boy Game Boy prototype. Because Working Boy probably finds. Yeah, there we go. See this? Don't know where this picture is from. Bitcoinwithmoney.com. Well, okay. Don't go to that URL. I'm sorry. It's just whoever hosted this picture. So this came up. Actually, let's go to this one. This is a Blogspot URL. So, but yeah, as you can see, the Working Boy, it had like a little keyboard which you would attach to the serial port on the side, because again, you can just talk to basically anything with this thing. Red Your Futures made a video about it. Yeah, there was. So I've been preparing this little article for my blog where I actually talk about all the reasons that I'm relaying right now, why I'm going into this. And I also mentioned the Working Boy. Was it called Working Boy? I thought I mentioned it. I thought there was a YouTube link somewhere. There's a really good video on it about YouTube, which you can find here. Oh, I didn't add the link in yet. So this blog post is very much work in progress. But yeah, we're probably talking about the same video. It was a whole documentation about it, and one of the original Workboy, there we go. One of the original developers also came and actually sent him a working copy of this thing, as far as I remember. But yeah, it had a bunch of neat applications that you would find in that time for, like, you know, on PDAs and stuff like that. So there's the clock, there's the calculator, all these things. Okay. So, so my idea was then, okay, this is a system which is fairly contained. It has been around for a long time. I don't, when did it actually come out? Is it like the 30th anniversary or something like that? It's an old device, right? Came out a few years after I was born. Yeah. Yeah, it is old, okay? So am I. But the beauty of this is then a lot of things are already known in the homebrew scene. In fact, some of the internal programming manuals that programmers back in the day got also by now leaked over the internet, right? I'm not going to open this up and show you anything out of in there because I think this is like just asking for all kinds of trouble. But essentially, all you can find in there is also explained in these pandocs on gbdev.io, which is fairly comprehensive as well. There's a few other ones as well, which they link, I think, in the acknowledgements as well. No, maybe not. There was like... Maybe that's just throughout. Emulator developers may also be interested in this. So this is like the technical reference by Gekio.fi. I don't know. It explains a few things about the CPU as well, which is quite neat. Also how the boot ROM works and all this kind of stuff. So yeah, as you can see, the scene has been on it for quite a while. And in fact, there's also a multitude of emulators out there. One of them which we'll be using as well. I have not decided on which one yet. If you know a good emulator, let me know in the chat. I was thinking of the Visual Boy Advance, but that's simply just because I know it, right? I don't know if this is exactly like the best thing to use nowadays on Windows or anything like that. I don't know. Oh dear, where's the? Is there even a download somewhere? Like, I just want to download the latest version. Building. I don't want to build it. That's insane. Just give me an executable, please, somewhere. I guess if we look at tags and then a version, we must be. I forgot how GitHub works. I'm so sorry. No, it wasn't tags. What did I have to click tags? Oh, I have to click. Yeah, okay, sorry. Here we are, releases. Okay. Win x8664 sounds about right. What we want for our purposes, right? Let's see, open file. And it's just an executable. I love this. Oh man. Okay, let's put this in projects. Yes, we want to run it anyways because we totally trust this source. There we go, Visual Boy Advance. And now I think I can just where do I have? Okay, let me quickly hide my screen because I have to check where my ROMs are, my Tetris ROM and my Super Mario ROM, because those are the cartridges I own. So I made ROMs of it. So if we put Tetris in there, hang on, I need to. I do not want to play audio because that will be another grounds for a copyright strike. So let me try and disable it. And then if I put Tetris in here, it will just run it. Okay, so why I wanted to select Visual Boy Advance is because once I'm starting to do my own ROMs, it has some nice features like, well, like for example here, it has a memory viewer, it can view the palettes, it can view the tiles that are in memory right now, and it can also, see the disassembly. And you can also go to the program counter and then, also kind of step through. So if you see automatic update, you actually see what the GameBoy is doing at the moment, what kind of code it's running and all this kind of stuff. So that's neat. Eventually I want to write my own emulator, so which will be fun because I also want to learn how those are written and how those work. I will not be looking at any of the source code of any other tools. This is just me trying to do it on my own, learning with nothing more equipped but the manual and the website. Hope that makes sense. So that was a long introduction of what I'm trying to do. So yeah, I want to learn how a CPU works and how to write programs for it. So where do we start? So we know that the ROMs, so if we're going to projects, and let's take Tetris because it's just 32-kit, right? We know that on any ROM we have this particular section here from 100 to, well, 100 hex to 140 F hex is the header. But now we have like all this other stuff here, right? There's lots of other bytes. So what do they do? What does this even mean, right? So how can you have, going from this to this, right? How does this translate? How does this work? So basically, let's start simple. What is a byte, right? A byte is essentially just a number, right? So, well, more or less, it has a specific width, and it is quite limited in the range that it can go to. So a byte can usually go from 0 to 255, right? Um, Let me think about how I should explain this. You know what? Actually, let's start even lower. Let's start with a bit. So, a bit can be represented with two values, either 0 or 1. And you might have heard, at some point, if you have no idea about programming or anything like that, you might have heard, oh, computers deal with zeros and ones, right? It's just a bunch of zeros and ones that they translate to whatever you see on the screen, like magic, right? So this is what we're essentially talking about. It's a bit. A little bit. Exactly. So, um, so it can go from 0 and 1, and essentially what this represents is a state, right? So, for example, if we talk about a light bulb, it can either be off, right? Or it can be on, so it shines. And we can translate this off and on basically as just numbers, 0 and 1. So a bit is just that. Some kind of signal that indicates, hey, there is some power on there, or there isn't, right? Um, how does it translate to a CPU? So for example, let's take the GameBoy CPU, right? So here we have the CPU. And you might have heard those terms like 8-bit, 16-bit, right? Or 64-bit in terms of desktop computers. And the CPU, that it can deal with like a specific number of bits. So the Game Boy CPU is an 8-bit CPU. All that means is that this CPU can handle 8 of these little bits, 8 of these signals at a single time, right? So let's say we have 1, 2, 3, 4, 5, 6, 7, 8. 8 of these bits going into the CPU. Now the CPU can do something with that information and then spit out, in theory, it's not quite like that, but we'll get to that. It can basically handle 8 bits at a time. So what does at a time mean for a CPU? Well, you might have heard a CPU has something like hertz or megahertz, gigahertz these days, right? So my desktop CPU is like 3.6 gigahertz. All you can translate hertz to is basically the amount of operations. So 1 hertz is the amount of operations a CPU can do within 1 second. 1 hertz is equivalent to 1 cycle per second. Now, if a machine has, let's say, 500 hertz, what does that mean? Well, it basically means it can do 500, well, it's not quite 500 operations per second, but okay. It basically has 500 cycles per second. It can do 500 things within a second. So I'm not sure if you have heard of SI units or anything like that, but basically if you have 1,000 hertz, you can write that in the short form as 1 kilohertz, right? And then you have 1 million, 1, 2, 1, 2, 3. 1 million hertz would be 1 megahertz, right? So a 1 megahertz CPU, well, what does that mean? Well, it means it can do a million things within a second, right? So if we're talking about gigahertz in our today's machines, right? So any desktop computer with, let's say, okay, let's make it easy. Let's just say, whoops, 3 gigahertz, right? That would be 3 0 0 0 0 0 0 0. So, uh, uh, so in English, is that a billion? Yeah. It can basically do 3 billion things per cycle, per second. Sorry. So that's quite fast, right? Um, from going from just being able to do one thing per second to then, let's say, on a megahertz where you do a million things per second, right? And then you go even higher into the gigahertz range, which, yeah, our CPUs these days are extremely fast and can do a lot of things within a single second. So, and back to the bits. So, an 8-bit CPU just means a CPU can act on 8 single bits within one cycle at a time. So basically, how fast is the GameBoy CPU actually? I do not know that off the cuff. Hang on. GameBoy CPU. I know there was some things. So it in theory is 4.1 megahertz, right? So it can do 4 million things per second. But I think it's bound by the memory speed, so it's actually a bit lower than that. But I remember from one of the talks there's some debate around that, whether it's truly a 4 megahertz CPU or not. We don't need to be worrying about this. All we know is like, okay, it's roughly 3 megahertz, right? Sorry, 4 megahertz. So it can do 4 million operations on 8 of these single bits in 1 second. So how is that helpful, right? If you remember what a ROM looks like, so let's zoom in here. So basically, I thought the zooming would. Okay, kind of works. Sorry, this tool is a bit new to me as well. So if you remember our ROMs, there could be 32 kibs of data in a ROM. Let's just ignore the header bits, right? The few bytes that are there for the header, which are not technically code, but are part of the ROM. But let's just assume we had a full 32 kilobits, kilobytes on this tool. You can see when you open the ROM, it's basically broken up in little bytes. So what is a byte? I'm sorry if I'm going a bit too low level here with this stuff. I just want to reiterate over all these things. So what is a byte? Essentially, 1 byte is a collection of 8 bits, right? So as you saw here, the GameBoy CPU is an 8-bit CPU, which means it can act on 8 bits at a time, which basically translates to it can act on 1 bit at a time, 1 byte at a time. So when we open those ROM bytes, and there's like lots of little bytes in there, right? Basically, it can act on one of those at a time. And these bytes have a special encoding, right? Um, so usually they can represent numbers. Um, so, um, well, they can represent numbers, or they can represent, whatever you want, really. It's just a matter of how you interpret those bits, right? Um, so let's say we have 8 bits at a time. 1, 2, 3, 4, right? And so they all basically for the CPU have a special meaning. So for example, 000 could be do nothing, right? Now we have, for example, 000000001. That could mean something to the CPU as well. For example, I don't know, do whatever, right? Uh, and that goes on like this. So whenever we have like a different number set, it means something to the CPU. All the CPU is doing at the ROM is it goes to a specific location in the header where it finds out the starting address of the game. Let's say it would be right here on the address. And then all it's doing is, hang on, I have to get my dog to lay down again. Okay. So all the CPU is doing is it goes from this position onwards through all the single bytes in the file, reads them out, and tries to interpret them, right? So if we go back to the window here, for example, let's say the starting address is on 500 hex, right? Our CPU is now here, and it reads hexadecimal C0. That means something to the CPU, and it will do something accordingly. Then it goes to the next byte. C9, it also means something to it, right? And it does that for every single cycle, basically. And we know it is roughly 4 megahertz, which means it can do 4 million of these little things, roughly. Not quite. We'll get to that in a moment. Per second, right? So it reads a bunch of these per second and does something. So if we would want to develop our own Game Boy game, we basically just need to know what those little byte commands are and what they're doing, and just write them into a file. And then the Game Boy would do something accordingly. And if you look in the Game Boy manual, there is basically a whole list of commands and what those single bytes mean. I actually have a file here where I went through all these instructions, right? And what they mean. So, for example, hex 00, which is these 8 bits here, and I kind of have them split up a bit weirdly here because this is how the Game Boy manual splits them up. But I think easier to understand would be if you put them in a nibble, because a collection of 4 bits is called a nibble. Get it? You take a byte, or you take a little nibble. Whoever came up with these, I don't know. But a Game Boy manual specifies them like this. It groups them in 3 bits, another 3 bits, and then 2 bits at the top, right? So if we ever encounter a 00, then it basically is an instruction to the CPU that it has to do nothing. So if we were to look for 00, okay, this is not how the search works. Interesting, but I kind of went through the right thing. So as you can see here, 00 if the CPU were at this point and it would find the 00 here, it would basically mean like, do nothing. Just go to the next byte. Now this takes one cycle out of your 4 megahertz, right? So this will take 1 hertz essentially within that second. Then we have the next one, for example, 0, 1. So if you look at the bits, we have 0, 0, 0, 0, 0, 0, 0, and then a 1. What does that mean? Well, this is where it kind of becomes tricky, right? Because there's this whole table of commands for the CPU to do. Like, you see, it goes all the way to 1, 1, 1, 1, 1. Like, where this is a specific instruction for something for the CPU to do. There's some instructions that are empty, right? And what kind of instructions are they? Well, we get to those like individually at some point, but basically what it has is like add, right? Add 2 numbers together. So you can instruct the CPU to add 2 numbers together. Call, you can instruct the CPU to jump, or here with JP, to jump somewhere else into the code. So if you find a D2, for example, is this how this works? Hex values. I can search for hex values. There you go. Okay, a D2. So in this ROM file, if we found a D2, this basically instructs the CPU to jump to somewhere else in this file and continue execution from there. Hang on, I have to put my dog on the bed. There we go, little one. You happy? No? Oh, but I need to lay down there now, I'm sorry. Okay. Being a dog parent is not easy. Okay, so the takeaway I just want to give you is all of these numbers in the ROM mean something to the CPU, right? There's a few other differences because what about graphics, right? Well, you can just put graphics in here as well and code it as just bits and like as bytes essentially. So I don't know, if you like take all of this could be an image, right? It is all about how you interpret those things. If the CPU would go over this image, it would not know that it is an image because the CPU doesn't have a concept of an image. All it has is its bytes, and it knows how to interpret those bytes as a specific command of what it's supposed to be doing. And this is essentially how any CPU to this day works, right? So your desktop CPU is doing the exact same thing. If you open an executable on your machine, let's say, well, let's take this emulator, for example, right? So if I open this one, you know, it's exactly, well, there's a bit of formatting similar to the GameBoy header, like there might be a header involved, right? For example, here there's like a DOS header that tells Windows that you cannot run this executable under DOS, because DOS is still a thing apparently. Well, backwards compatibility, which is actually, it is great. I mock it a lot, but it is actually great. But essentially all those values in this huge ass executable here is exactly the same thing. It's just instructing your CPU what to do, right? Similar to a Game Boy ROM. Like, there is no difference whatsoever, except that it's different instructions because it's a different CPU. For example, as you know, a CPU might act on 64 bits at a time. Are you trying to get out? Sorry. Come on, you can get out. Okay, so for 64 bits at a time, right? So what are 64 bits at a time? Well, it's 8 bytes at a time, right? So 1, 2, 3, 4, 5, 6, 7, 8. So these 8 bytes at a time to a 64-bit CPU mean something very specific, right? Well, there's all kinds of other things in place in modern CPU systems, so not every instruction is exactly 64 bits wide, right? They can have different widths, but that's a whole other thing that we don't need to worry about. We're trying to be very simplistic with the Game Boy and only deal with 8 bits at a time, which is again why I chose this system, because it's quite easy to wrap your head around. There we go. It's not a complicated instruction set, is what I'm saying. Okay. So we know that every byte has a special meaning. So what we now could do to program a Game Boy game, right, is, well, let's just create a new file, right? And then figure out what we need to be doing. So for example, I don't know, let's say we want the CPU to do nothing for a bit, right? So we just add in 0, 0, 0, 0. What? Okay, 0, 0, right? And then we want the CPU to, I don't know, let's say we want to increment something, so it would be hex 14, right? So we type, oh, no, that's not how we type it. We type in a 14, and then, you know, we go a little bit further, and let's say we want to add 2 numbers together, so this would be hex 80, so we have to type in an 80, right? This is how you would program a game, essentially, right? And this is what people have been doing way back in the past with the very first computer, where they just had, you know, switches where they could switch on specific bits of a byte, right? And then press a button, which then would execute that single instruction. And then they would, you know, flick the switches again to put in the next instruction, and then press a button to run it, and then flip them again, and all this kind of stuff. Now, obviously, you don't need to do that anymore, and writing a file like this, although it is possible, you could write a game like this with essentially just a hex editor and, you know, this table here, and just punch in the numbers one by one. It is quite excruciating to do. So this is where something like an assembler comes in. What is an assembler? Well, because all these instructions have a very specific meaning, what you can assign to them is a mnemonic, right? So, for example, do nothing can be described as no op or nop, right? I don't know, increment a number by 1. Well, we can describe it as inc C, right? Which would translate into this code. And this sort of becomes a more readable human language suddenly, right? It's easier to reason about than just some hex numbers on the screen. And you might have heard of the term assembly language. So essentially what that means is, actually, let me show you an example. Game Boy assembly. There's a GBASM tutorial on gbdev.io again. Fantastic. So let's look at Hello World. What would that look like? It's their own stuff, but there is an ASM file. So yeah, so as you can see, this is basically what assembly looks like. It is code that you can easier reason about, right? You have a load instruction here, LDA0, right? Something here. Obviously, we cannot read that yet. We don't know what any of these things mean, right? There is some words here that you can reference here. But JPC and then something, or LDA and then, you know, a 0, we know what those are based on this table right here. So we can actually look it up. LDA and then some number like 0, that would translate to 3E, right? So all an assembler is basically, it tries to take away the tedium of writing these hex codes or these bits individually into a hex file And you can just have essentially a text file where you sort of write human readable code that the program then goes through. It sees, for example, this instruction here and just spits out the corresponding bytecode out of it, right? So you as a programmer would write this kind of text, run the assembler over it, and what it would spit out is, okay, I had an alarm set for some reason. What it would spit out is, you know, this kind of ROM file, this kind of binary file that the CPU can actually understand. So as a human, it's easier to understand this kind of code, and what it spits out is this binary nonsense here. Nonsense to us at least, but what the CPU understands. It takes a long time to like learn all these commands and what they mean and things like that, so I'm not sure I will be going through that in the stream. I just wanted to sort of give a preamble for people that are not familiar with assemblers or how a CPU works, just to give a little bit of context. I hope that was somewhat useful, somewhat understandable. So what I want to write in this stream essentially is an assembler, right? So I want to take a text file that includes to us some gobbledygook like this and spits out something that the Game Boy CPU can understand. And because I showed the emulator before, you can actually see when you go to the disassembly and you go to automatic update, whoops, pardon me, and you can actually say pause. As you can see, what this thing is doing is it looks onto the hex code that the Game Boy is currently at and tries to show you what kind of instruction in assembly it's trying to do. And if you just click next, you can actually see and follow step by step through what the Game Boy is doing in every cycle, right? So see, it's just going through the file one by one. It's jumping around the file here and there. What those jumps are, I'll get to explain at some point as well, probably. But yeah, it's just doing all of this to then, you know, produce the output. So if we now go to, instead of pause and going through frame by frame, let's just reset. And you can see how fast this is, right? How many of these different instructions is actually calling. You can see, like, we can't even read what it's doing, right? And that's because it's doing like close to 4 million things per second, right? One player, there we go. Right. And you can see how it's still jumping like through the code and doing certain things and like, yeah. So I've been not telling you any lies. This is exactly what the CPU is doing. An emulator essentially does the same thing as the Game Boy CPU. It tries to do the same thing. It goes through the binary ROM file that you provided and tries to read in roughly the same time as the Game Boy would, trying to read all those commands one by one, and then just emulating the output of what the Game Boy would be doing. So in this instance, rendering onto a Win32 window and sort of giving you roughly the same output as the Game Boy would. So anyways, let's start writing an assembler. Let's call this GB assembler. Why not? Let's be very basic, right? So my goals are basically, I want to be able to write very basic games with the assembler that I'm working on, and it will be just focusing on the most basic thing the Game Boy supports. In this instance, 32 kilobytes ROM files without any extra RAM or anything like that, because going into all this just complicates things from the get go, right? We want to start simple. So we will be able to produce 32 kib ROMs. We will be able to parse all instructions. And okay, where do I go with this explanation? Because as you can see, there is some things that are not exactly Game Boy instructions, like for example here, wait v blank, that's something someone else specified. Those are labels and all this kind of things. I'll get to those and explaining how these work once we reach that point. But for now, all we need to do is, okay, an assembly file is usually donated with .asm, but all it is a text file, really. You could just name it .txt or anything, right? It's just basically a file with a bunch of text that we're going to step through and then parse one by one, and try and make sense of it to then output a Game Boy ROM, right? So let's create a new project and just start, I would say. I'll try to explain things as I go along. I kind of already know what I need to do, right? So apologies if I'm just jumping ahead or back and forth a little bit. I would love to do a kind of video series for beginner at some point and upload that to YouTube, but it takes a bit more planning and work to do that than just doing this ad hoc in these streams. In the streams, I really just want to explore how easy or difficult it is to write your own tools, to like write programs for other machines, basically develop tools and all this kind of stuff. And I'll be experimenting a lot here and just trying out different things. And hopefully, you know, if you're watching this, hopefully you get something out of this as well. Okay. So let's create a new console application and let's call it Game Boy assembler. Straightforward, there we go. This is C++, but we do not want C++. What we want is just what the hell? No, that's not what I wanted. What? Oh, apologies, I kind of screwed something up there already. Let me look in the CPP file is still there. Packages config we don't need. Okay. Let's just add a code file and it will just be main.c because we are using C. And let's change those settings to actually make sure we're using C, and what we're using is C17, the new standard. Do we use a Unicode character set? I mean, for the application itself, yes, but for reading files, probably not. What I want to do is read byte by byte. We will be supporting Unicode in those files, but it's done a bit differently. Let's put it this way. Actually, here. No, that was all correct. Okay, all configurations. C. Where are we? Assembler output. Yeah, sure, we can have that. Actually, that's a good point. So not LibreOffice. Thank you very much. So this hex file, if you actually open it and look at the raw bytes, what this is usually called is machine code, right? It's codes that a machine, in this case the CPU, can interpret and do something with it. The step above that to produce the machine code is assembly code. And I talked about how executables on an x64 machine, or your Windows or Mac desktop or Linux or whatever you're using, are exactly the same, right? There is no real difference between those things except what those bytes are and what those commands are. And you can see that by, for example, if we go to the previous tool, the GB header extractor, and we build it, what you can instruct. Oh, did I not do that here? Oh, I did not. Okay. Let me just do that real quick. No, I did. Assembler output. Where are you putting the assembler output then? Did I not do this for all configurations? I did. I just wanted to show you that when you build C code on your machine, you can also generate the assembler output to actually show you what the assembly would look like. Because C is just another layer, right? Assembly is like very basic mnemonics for the machine code. So you don't need to actually write all the hexadecimal bits. And then C or other programming languages are just another abstraction in that sense, where it's even easier for us to like reason about the code and write code. And then you would put it through a compiler, and all the compiler is doing is essentially creating that machine code. And then you can take that machine code and interpret it as assembly code if you would like to. For some reason, I do not find the assembly files, even though I know they're being generated. Really? Where would those be? Nope, certainly not here. They probably have a different file ending than I assume them to have. Is this it? Ah, this is it. Okay, they don't name it .asm, they name it .cod. But essentially what you can see here is, so this is my static website. Actually, let's go to the GB header extractor, since this is the program that we wrote on this stream. If we open the COD file, we can see it's very similar to whatever the GameBoy assembly code was, right? So we have jump. Yeah, we have a bunch of different things here. Why is that? What? That was weird. Yeah, so for example here, J and E is like a mnemonic for something specific. Test is a mnemonic. XOR is a mnemonic. This is the bytecode that's essentially produced, so the machine code. So 48 hex, 85 hex, and C9 hex translate to test RC RC, right? So if we look in our executable in the hex editor and look for this little thing, we know this is what the CPU will be executing. So no real difference between desktop PCs and Game Boys. Just let that sink in for a second. So yeah, we want the assembly output, and there is somewhere where you have to say compile as. Yeah, compile as C. Cool. Yeah, this is all right. Let's just go to debug, because what I also like to change is for the runtime library, I do not want to rely on DLLs, even though that would make the executable a little bit smaller. What I want to do is just use the static library and like compile it into the executable itself. And we can do the same with the release mode. So we can say, instead of multi-threaded DLL, we just go multi-threaded. The runtime is always multi-threaded, unless you specify specific command line options to not make it multi-threaded, which we will be doing. And we can just copy that from our previous tool, right? So let's just use the same thing. It's main C, but it is for the GB assembler. Version 01. And we have created this file on the, what's today? The 7th. Cool. This is the thing that I mentioned. So in order to use single-threaded mode for operations, because I do not care about multi-threading with this at all we're doing is processing one file at a time, right? It's usually fast enough anyways. So you can define this this thing, CRT disable perf crit locks, before you like include any of these headers, and then it will just use the non-multi-threaded version of some of the functions. I explained this in previous streams already, so but actually let's just copy all of these, why not? Do we need Windows? So I'm gonna copy my typedef H, because these are like convenient typedefs for me that I like to use. I do not like using this unsigned char and type it all out. U8, U16, U32, or U64 is like easy to remember for me, easier to write out. So I'll be using that one. So I'm using wmain here because in the previous project we learned that this is the Unicode version of it, so it uses wchar t for all the command line arguments and things like that, because Windows operates in UTF-16. So what are we trying to do? We are, well, let's say we are trying to open a file called program gbasm. We just assume if we want to use our assembler, there always needs to be a file called program.gbasm, which will include our GameBoy assembly code, right? And then we're just basically trying to read from it. Okay, so let's just do okay, I would use wide f open if I were using the C runtime. How would that translate to Windows? So is there something like open file? Doesn't seem to be open file. Interesting. Do I have to use create file? Creates or opens a file or IO device. The most commonly used I/O devices are as follows: file, file stream, directory, physical disk, volume, console, buffer, tape drive, communications. Oh shit, okay, so you can basically do everything with this. To perform this operation as a transacted operation. Okay, what are transacted operations? I do not know, but that's something to find out. And I like having like this little file here called questions.md where I'm just writing out questions for the future that I want to get answers to. Right now, I think this just distracts from what I want to do. So Windows transacted file operations. Actually, what are Windows transacted file operations? All right, let's not worry about that for now. So create file has a lot of arguments, right? Okay, so first of all, what we need is I included a lot of these already, but we might not be needing them right away. So let's just comment those out until we actually need them. I think we do need stdlib for wmain though, but I'm not sure. Let me see. What if I try and rebuild this? Debug mode, please. Rebuild. Okay, that just works. So if I just run it. Okay, cool. Okay, let's include Windows. And I mentioned those defines before. Similar to here, with defines like this, before you include a header file, it's basically just to give some control to your program of what you want to include from the library and what you don't want to include, right? There might be a bunch of functionality or code that you do not want to include, but if you do this, it would still do that, and it will probably increase compilation time because it will include all the code that you're not using. Only then in the linker to try and figure out what it can strip out because it's never used and things like that. Or sometimes it might not be even be able to strip out certain things. So this is just a way to like make sure stuff gets excluded. Right, we have my own library, which is the type dev. Okay. So create file. So I removed the W here because create file is essentially a macro that either calls create file W or create file A. We should be using create file W because that is the Unicode version, so UTF-16. A stands for ASCII, so it's kind of annoying that they said like ASCII and wide because it would be narrow and wide, but yeah, whatever. And depending on what flag you want, you can just use that macro, and if you switch, Unicode support or non-Unicode support in your application, it would just magically work, although that never really does magically work, but whatever. Let's just assume it does. Anyways. Okay, so we have create file. What are we taking in? We're taking the LP file name, which is an LPCWSTR. Now, what are you? You are a const wchar pointer. And I love how they have it defined for const to make it const. Awesome. And a wchar is just a wchrt, 16-bit Unicode character. Fantastic. So this will be our file name. Let's check the documentation if there's anything special we need to be watching out for. Okay. Do not assume case sensitivity. Yeah, makes sense. So there's some characters that are not allowed for file names. Okay, it's fairly straightforward, isn't it? Well, see, we don't need to worry about this, right? Because for now, we will be hard coding that anyways. So let's make a to-do. So we just have a const, a w char t, pointer to it because it's a string, so multiple characters, and we are naming it. Let's just call it input file name, and this is a long. Our input file name will just be any assembly file we specify here. So let's just create one in here. Why not? Can I create folders from this program? New folder. Cool. Oh, folder name down here. Okay. Let's just call it GameBoy assembly. Sure, why not? And plug in this file there, which will be our program.gbasm. All files, save. Sure. Cool. So we have a program.gbasm file. We should probably now open containing folder, and then we can say copy as path and add it in here. And of course we need to encode the double slashes, sorry, backslashes. Okay, so this will be the file we're dealing with for now. It's hard-coded in there. It's just, you know, while we're developing this application, we do not want to worry about like command line arguments and passing in the right file. We just hard-code the file and just try and use it. So, create file returns a handle, which is just a void pointer. Okay. Sure, so we have a handle, and this is, I guess, input handle. Right, calling create file, and the first argument is our file name, which is just input file name. Cool. The next one is a D word. What is a D word? An unsigned long. Okay. And it is called desired access. So let's read about that. Desired access. The requested access to the file or device, which can be summarized as read, write, both, or neither zero. What? The most commonly used values are generic read, generic write, or both. Okay, so the handle it returns will be used for other file calls to then do certain operations of the file. So for example, if we're reading from it, we probably need to have the input handle. So similar, if you know, with fopen, I didn't include stdio, did I? Let's just include it for now. So fopen returns this file struct right here, the pointer of it. And whenever you want to read from a file, okay, let's expand the macro. You see right here, one of the arguments is the file stream, which is just the file struct. So that is essentially the file handle, right? So in Windows, we have exactly the same thing. Instead of calling it file, it's just the generic handle, which is just a void pointer. So we don't even know what it is, right? It's some internal thing that Windows selects. I mean, since it's optional, let's just ignore it and hope that Windows does the right thing. And we're just going to specify generic read because that's all we want from the file, right? We want to read from it. So generic read for the desired access, right? Which is this number right here. Okay, next we have share mode. If this parameter is 0 and create file succeeds, the file or device cannot be shared and cannot be opened again until the handle to the file or device is closed. So effectively what this means is if share mode is 0, we're basically just saying to the operating system, hey, I have exclusive access to this file. No one else can touch it. So basically, if we want to play nice for the share mode, we can do file share read. So this would, since we're just reading from the file, it makes no sense to block reading from other applications that might access it at the same time, right? I suppose. So security attributes we learned about, those are optional. So we're just not going to deal with that at all because security on Windows is just something I do not want to deal with right now and have no idea about. So let's just specify this as null. Then we have creation disposition. An action to take on a file or device that exists or does not exist. Okay. Create always. Creates a new file always. No, we do not want that. Create new. Creates a new file only if it does not already exist. No, we do not want that either. Open always. Opens a file always. If the specified file exists, the function succeeds and the last error code is set to error already exists. Why do you set the error when it succeeds? That's interesting. If the specified file does not exist and is a valid path or writable location, the function creates a file and the last error code is set to 0. No. Opens a file or device if it exists. If the specified file or device does not exist, the function fails and the last error code is set to error file not found. This is exactly what we want. Cool. So open existing. Bam. Now we have flags and attributes for that file. It doesn't strike me as something we need to set at all when we're just trying to open a file for reads, so null. Okay, and what is template file? Wait, no, it's probably not null. It's a D word, so it should just be 0. Okay. Then we have template file, a valid handle to a template file with the generic read access right. The template file supplies file attributes and extended attributes for. Oh, okay. So you can copy the attributes from a different file that already exists on your system by specifying the template file here. And it is a handle, so you need to open that file first, get the handle of the file, and then pass it in here so it can use the same attributes from that. Since we do not have that, and handle is a null, is a void pointer, we can just specify null here. Okay. So this should be our file. Now we need to make sure that actually worked. So how do we do that? Return function. If the function succeeds, the return value is an open handle to the specified file. Okay. If the function fails, the return value is invalid handle value. What is invalid handle value? It's a long, which makes sense. Long is, sorry, long pointer, which is an int64. Because it's an int64 pointer, it's -1, so it will be translated as 0x 1, 2, 3, 4, 5, 6, 7, 8, essentially, right? Which basically is an invalid pointer. Okay. Cool. So we know if input handle is this, we fucked up, boy. What should we do? Let's just go classic puts, right? Create file failed. We don't know for what reason yet, right? It's just an invalid handle. We don't know the reason. So let's just print that. Otherwise, let's just say create file worked. Yay, hooray. I find it so unintuitive that to open a file you have to call create file, but I guess it's like create the file handle. I don't. Let's not, complain too much about an API that's probably older than I am. I actually saw a tweet recently about someone who worked at Valve with someone, and they were like trying to use a specific Windows API from the user 32 DLL or something. And that guy really was like, I hate this API so much, it's rubbish. And then one of his colleagues turned around and was like, yeah, I'm sorry about that. I was 19 when I wrote it. I was like, all right. I find that to be funny. So anyways, so since this is similar to fopen in C, I guess what we need to do is also close the file, right? Because now we open up the file handle, but once we no longer need it, we need to close it. So, is there a close file? When an application is finished using the object handle return by create file, use close handle. Right, okay, so it's more like a generic close any handle sort of thing. If the function succeeds, the return value is non-zero, right? Because it's a bool. I guess just use close handle. Close handle. And we're closing the input handle. Now, it returns bool. Do I really care if this fails? So if this fails, let's actually let's do it this way, right? success down here. Oh dear lord, where's it? It's an stdlib, isn't it? Yeah, okay. Okay, so we're calling create file from the Windows API with generic read. We want to be able to read from multiple instances. Why not? Because we're just reading from the file. We only open if it exists. Okay, so let's try the arrow path first, right? Let's just add some characters in here because that file does not exist and see what happens. Okay, what did I do wrong? I didn't put it as a startup project. It actually starts a different project. Fantastic. There we go. Okay, create file failed. And even though the handle is an invalid handle value, if you pass it to close handle, it will still succeed. So I think we can probably just ignore the return code. Yeah, let's just ignore it. Okay. Whoops. So here we're closing the file handle. That's okay. Now let's try open it like that. Create file worked. So the file is open. Fantastic. We open the file with the Windows API instead of using fopen from the C runtime. Okay. So we've opened the file and now we can actually start parsing it. If we get an invalid handle from the Win32 API, we also want to print out an error, right? To see what actually went wrong. So for that, there is this get last error message. And I've been using that before. So you would get the last error code with get last error. And then what you can do is call format message, where you pass in the error code and it will then spit out the right error message for you to see what actually went wrong. So I'm just gonna be sneaky here and just copy the code that I used in the previous tool that we wrote for the GameBoy header extractor. And let's just see, I have print Windows error right here. So we can just steal that. That's why rewriting things, right? It has a bit of formatting involved and stuff like that as well, but essentially you can see what we do here is get last error and then call format message and free the message buffer as well in the end after we cobbled together the message and printed it out on standard error. Okay. So we can just do that instead and say fail to open input file and what is our file? Well, it is input file name. Else. So now if we have a invalid file name, we should actually get a proper error out of this if it actually compiles. Oh, see how I always forget. You want your definitions up here. Okay, so fail to open input file, and now if we actually have an issue, fail to open input file, and we print out the input file, the system cannot find the file specified. There you go. This is the official Windows error message. Cool. Okay, so we got that basic going. And now what we need to figure out is, okay, we want to read from the file and then parse it, right? Um, so let's think about this. I know from file reading, and this is what fread does as well, um, it has a buffer in the background, right? Which is exactly the same size as the sector size of your hard drive. So the sector, well, your hard drive basically is optimized to read in sectors, right? So I know for a fact on my hard drive it's 4 kilobytes at a time. So I should access this file in 4 kilobyte chunks at a time if the file is indeed that big. If not, we just read however much we can out of that file, right? So probably what I imagine what we would have is something like U8, which is unsigned char, right? We have a buffer. Let's call it input buffer. And we want it to be, I think that's 4 kibs, right? Actually, let's make sure. There we go. Yes. So, and now we want to fill this with data from the file. So I have no idea how to do this with Windows. With the C runtime, we would just do fread, specify our destination buffer, which would be input buffer, right? The element size would be size of U8. The count we want to read at once would be the 4 kilobytes right here. And then we would need to specify the file stream, right? Which we do not have because I haven't used the C runtime now. And what we would get back is the size we have actually read from the file. So either it would be 4 kilobytes, or it would be less than that because the file is smaller, or it would be 0 if we are at the end of the file stream, right? So, and since this just translates to calling the Windows API at some point as well, surely that must be able to do with Windows API directly, right? So let's figure out how to do that. So we have create file, and I saw before there was something like read file down here somewhere. Read file. Reads data from the specified file or input-output I/O device. Yes. Reads occur at the position specified by the file pointer if supported by the device. This function is built. Okay. Blah, blah, blah. I mean, this seems to be doing exactly what we want, right? So let's copy this definition and plug it right here. So it returns a Boolean value as the read result, so whether that read succeeded or not. And then the first thing is the file handle, which we have. That is our input handle. So we're acting on the file that we just opened. And then we have the LP void buffer, which is out. So this is the buffer we actually want to put stuff in. And LP void is just a void pointer. Fantastic. I love these remnants of like near and far from like 16-bit Windows. Backwards compatibility for the win. So, okay. I guess what we just do is say input buffer, right? Just pass it in like that. It's the address of our input buffer. Next, we have the maximum number of bytes to read. Well, that will be our 4 kilobytes, right? So let's just put that in here. The maximum number of bytes to read, yes. And then we have a number of bytes to read again. A pointer to the variable that receives the number of bytes read when using synchronous hfile parameter. Read file sets this value to 0 before doing any work or error checking. Use null for this parameter if this is an asynchronous operation. No, we do not deal with asynchronous operation at all. We just want to be very straightforward, right? I told you I do not want to do multi-threading or any of this kind of stuff. Let's just be as simple as possible for now. So this will be essentially the same as whatever fread returns, right? So this is an LP D word, which is a pointer of a D word, and then D word is an unsigned long. Okay. Well, we can just use D word, why not? And bytes read. I mean, it is set 0 automatically, so I think what we can just do is this and get the address of that. Okay, overlapped. What is this? Pointer to an overlapped structure is required if the file parameter was opened with file flagged overlapped. Yeah, we have not been using that. Don't even know what it does. Do not care, right? So we can probably just set it to be null. Yep. Okay. Cool. And then instead of doing this, let's make this a define because I like defines. Input buffer size is 4 kib. And use it like this. Ideally, what I would like to do is, and I've done this with my static website generator, is try and figure out what the actual sector size is of the hard drive we are reading from. And that way you can adjust the buffer to the exact same size as that. But that overcomplicates things right now. So again, let's keep it simple. Read results has a value that needs to be examined. Yes, we're getting to that now. If the function succeeds, the return value is non-zero. Cool. If the function fails or is completing asynchronously, the return value is 0. To get extended error information, call the getLastError function. Fine. We shall do that. Let's just read 4 kib once, right? Okay, so this needs to go up here actually. And let's put this one up here. Okay, if read result is false, then we print a Windows error, and we say fail to read from file, and then we have the input file name. Okay, so at the moment the file is empty. If we go program TBASM, nothing in there. So let's see what happens. Whoops, I did not change the file name, but we can see it cannot open the file, and then we're trying to read from it, and it fails because the handle is actually invalid. So that at least works. Okay. Cool. And it just manages to read, but let's inspect what it actually read, right? Bytes read, 0. Because there's nothing in there. Cool. Now the question is, if there's something in there, how do I determine whether the file is completely read or not, right? So, I guess what we can do is say while read file let's not complicate things like that. Let's just make a second call actually before we go into the whole looping bit. Right. Let's just see what happens if we're trying to read from the file twice. It just works. Okay. So after the first one, read result is true and bytes read is 0. And then we do the second read and it's still true and bytes read is 0. Okay, so from that I gather that, you know, if we're reading from a file multiple times in a row in those 4 sector chunks, once we actually reached the end of the file, the read file will still succeed, but it will return us a bytes read of 0, at which point we then know we have reached the end of the file. That is good to know. So let's do it this way. We have a do. Chuck this in here. And then if this is the case, something went wrong. And we could probably want to terminate the loop. And as long as bytes read is not 0, we're just trying again and again. Okay. So this should read the whole file. How do we test this? Let's just do the first read. We're getting indeed 5 bytes, and our buffer now contains test. Yep, we're reading again. It has succeeded, but it is now null, so we close. Cool. We have our basic file reading done. Now we should just try and interpret what we're actually having in this file, right? So what I like to do is, so let's imagine we have, this is line 1, this is line 2, this is line 3, right? How do I explain this? So if you want to start parsing a file, I think at least what helped me when I did parsers in the past, because I've written a few parsers already, not relatively good ones, but still, what helps if you start tokenizing the data that you have, right? And tokenizing basically just means go through the stream of bytes that you have, try to make sense out of these and return them as tokens. So, for example, let's say we have the following tokens. Let's say we have a word, we have a space, and we have a new line. Right? This is not part of the file, by the way. This is our file up here. So if we then would inspect the bytes that we're having, we would go through this, right, and do nothing because this is not a special token or character that we recognize as anything. But then we suddenly hit the space. What are we doing? Well, we're then returning, okay, we have found a word, which is this, and then we have found a space. And we have found the next word, which is, and then we have a space. And we found another word, which is line, space. We have one, which also counts as a word, because that's just how our tokenizer works, right? And then we go to the new line, which means we reached a new line token. So this is basically how you can imagine tokenizing. So in terms of assembly, let's say we have load value B into A, right? So this is what typically assembly code would look like. We can actually tokenize this as, you know, let's say there's a word followed by a space, followed by another word. We don't know what that word is yet, followed by a comma, followed by a space, followed by another word, followed by a new line. Right? And then instead of parsing like this direct data, we're just parsing the tokens and see if it actually makes sense. And this is how you can validate syntax, right? Because after word, you would like a comma somewhere here, whether there's a space or a space, comma, space, or a space, comma, right? You need a comma for these arguments. So for example, with a tokenizer, you can then see, right, if the comma token is missing, that's an invalid syntax, right? Because like this is not valid code. You want a comma there for the arguments or whatever. This is how you can think about tokens especially. So we just want to tokenize our data. The simplest thing to do now would be to just have a new line token, which we're looking out for. We're trying to find the new lines. And where exactly the new line in our byte stream is. And then the other thing we're just going to ignore for now. So we just have one token for now, and just try to see if we can read the new lines. Because assembly code, as you mentioned, it's basically formatted like this. So we have an instruction here, right? Maybe some arguments or not, we don't know. But then you have a new line where you start the second instruction. So basically assembly is structured in a way where you have one instruction per line. And you can see this by using the pandocs right here. Where was it? Hello world. Oh, I opened it before. So this is like an example GameBoy assembler code, like a hello world thing. And as you can see, essentially, there's like, excuse me, there's one instruction per line. There might be empty lines in between or whatever, but it's just the easiest thing we can parse as a first step. Try and recognizing lines. And then maybe we can print out where in this buffer the line starts and ends, and maybe have a separate buffer where we put the lines, because our code essentially works one line at a time, right? So this is our file buffer. But when we're actually trying to parsing the code, we're just working line by line. We're not going to overcomplicate it in any way. So let's just do that. That will be the next step. How do we go on about this? I mean, probably what we want is an enum with all the tokens first, right? So type def enum. Sender token. Let's do it like this. And what kinds of token do we have? Well, we have a new line. Yeah, why not? Okay. So essentially what that means, after we've read our data, we want to figure out where in the buffer we just read a line starts and ends. And one difficult bit, and this will be interesting if we have to deal with this later on, is so we're reading 4 kilobytes at a time, but what if a line starts at the end of this buffer, but we don't find a new line character, right? Then we kind of need to hold on to this data until the next read is done and then continue from there. So, but we'll get it. Okay. So what we're doing is, what would the simplest thing to do be? Let's just do a for loop, right? And we're starting from so we're starting from 0. We go on until the end of the buffer size, possibly, and let's just increment this. Cool. So now we're going through the buffer we just read, byte by byte, and now we're trying to determine what that byte is, right? So we can do a switch and say input buffer I, and if that thing is a new line character, okay, there's a bit more to this. I won't be dealing with Unicode just yet. We're just going to pretend this file only contains ASCII characters. At some point I want to have Unicode support, right? So if you have a UTF-8 formatted file, I want to be able to actually read that out correctly as well. That's not strictly speaking necessity. Most assemblers just work with ASCII characters and just deny Unicode out of the gate. But I want to support it just for funsies. Why not? Would be fun to have, I don't know, smileys in here, whatever. God knows. Let me put it this way. Unicode support is just the right thing to do in my mind. But for now, we're just going to ignore it. So much for that. Okay, let's just look for an Show new line characters. There's a bit of a mix between those, right? There's carriage return and new line feed. Actually, let me see if I can find. Oh my god. I always forget the order of these things. I don't want to use Stack Overflow. Okay, there we go. So yeah, on Unix, a new line character is usually LF, right? Windows is CRLF. There's a few other machines and things, sometimes LFCR, great. What is RS? Okay, whatever. Don't think we need to care about this one. RISC OS, okay, interesting. Basically, why we need to worry about this is because your assembler file could have been, coming from a different machine, right? Someone might have written it on Unix, like Linux or whatever, and then all the line endings would be LF. And if we're assuming the Windows line ending CRLF, then, obviously that would be wrong as well. If we just assume it's CR, or if we assume CRLF, yeah, you see, it kind of clashes, right? You kind of want to deal with all these different ways of encoding the line endings, essentially. Okay, so this would be a hex value 0A. That's for LF. Actually, we can make just quick defines for these. Line ending LF. Yep. CR is COD. So if it's either this or if it is CR, then we will be doing something special. Okay, I forgot the 0x in the hex values, my bad. And then we have CR and LF. So if it is actually CR, okay, to do, look if there is LF as well. Okay. So then next we can specify a start position. Line start, which in this case would be 0. And then we have line end, which we do not know yet. Okay, if we have LF, then line end. And do we want to include the line ending character, yes or no? I think we probably should include it. Yeah, let's include it. Okay, so line end is at position I. I kind of like being exclusive though. So I'll probably say I+1. here, line end equals I plus 1. And then we want to check for LF. So we can do I plus plus if it's bigger or equal to input buffer size. No, you know what, actually if it is smaller than that, so it's still in the valid range, our index is still in the valid range. If it is still in the valid range, we want to check if there is input buffer let's call it next. So if we have a CR, the next index, is it still in valid range? We want to check it, and if that is indeed an LF, because CR and LF can happen, right? Then we have a CRLF line ending, which means we should set I to next. And then we just say line ends at I plus 1. Okay. So this should find the line endings. But that only works for the first line for now, but that is perfectly fine, right? So let's just print it out for now. Line starts at %d and ends at %d. It's actually let's do LLD, right? Sure. And then we have line start, and then line end. Cool. What did I? That seems way too high. What did I do? What did I fuck up? Okay. /n. Okay, so the values are correct. Oh, I'm just looping through. Oh my god, I'm. Jeez. Apologies, brain fart. Okay, what do we do here? I guess maybe we should make this a function to get out the beginning of the line and the end of the line. I think that would make sense. Does it? Yeah, probably. Okay, so what do we call this? Need to include std bool if I want to use bool. Find new line. And we're trying to find it in const char, this pointer right here, in this value. And the output would be, actually we can make this a nice struct maybe. Let's not make this a struct for now. Let's just do two output parameters. We have a size t, which is the start index, and we have a size t, which will be the end index. Right. And we don't need to worry about well, it's not const char, is it? It's const u8. It's an unsigned integer. I mean, it is unsigned char in that instance, but we need to not worry about null terminating characters or how long this is. Well, we kind of do need to worry how long this is, so what we should probably do is max size. Yes. Okay. Then we can just copy this one. Actually, copy this, right? So we're starting from 0, and instead of input buffer size, we check for max size, and instead of input buffer, we have value I, and then we have end index, and if we found the end, we just say return true. I mean, start index is not necessary because we know the start based on the buffer we pass in, right? So that will be at the right location already. And then we have this one, and if it is smaller than max size, and then we have value next. And then call this end index. Right. Otherwise, we don't find a new line character. Okay. So here, what we want is input buffer. Max size is input buffer size for now, because we're just looking for the first new line. We're not trying to do this in a loop for now. And what we set is the end index. So just line end. And Whoops. And I wonder if we don't find it, if we just set it to null. That seems like the right thing to do, maybe, yeah. I'm not going to bother with null checks for value to see whether value is actually a valid pointer or anything like that, because at the moment we know it's valid, right? It's our own code. This lives on the stack. That pointer will be valid. I'm not a fan of like big defensive programming, so it would be different if this was like an API that I'm exposing to like some users. So if you're writing a library and actually want them to use the code, then by all means, please check whether this is null or not. But for this, I don't care. So if this failed, then we can just say no new line found. Actually, just that's right. Otherwise, we found a new line. I see. This gets me all the time. Okay, this is still wrong. Right, because we haven't set the value. Need to dereference it, right? I'm not trying to set the pointer. What I was doing here was setting the pointer to like a memory location instead of actually changing the value. My bad. So now, there we go. Line starts at 0 and ends at 16, which will be, well, technically the last new line character is at 15, location 15. The reason why I like to do the exclusive end is just because it's easier to use in like for loops, because you can then do this like is smaller than this, you know. Don't have to like do +1 or think about it, anything like that. It's just, I basically like to have exclusive ends. That's just my preference. Okay, now what happens if there's just one line in here? No new line found. Right, because this is the end of the file. I know I already defined this token enum here and not using it yet. So let's just ignore that for now, right? Let's pretend it never happened. And let's just focus on finding out actual lines that we need to parse, right? So we have a find new line function now, which is quite handy. But there's like different scenarios we need to watch out for. So one of them I listed here. At the end of the file, there will be no new line character. So this is still a valid line. We just don't have a new line character, right? So, and then obviously there is the issue of, well, if we are at the end of the buffer, so we're doing this find new line multiple times, right? If we reach the end of the buffer, then it might happen that, okay, let's pretend this is like a huge file, right? Let's just do this. Imagine this would be 4 kilobytes, whatever. And let's say our new line is actually, no, that's maybe a bit too much. I don't know why this is red. Whatever. Is it because it's marked in? Oh no, it's NASM assembly. Whatever. It doesn't matter. So imagine this is like our 4 kilobyte chunk, and we have 2 lines here, and what we're reading into our buffer only goes like up to here, right? So this is the first chunk we read from the file. Now, as you can see, the new line is here, and this is not actually the valid, this is not the end of the actual line. But in our current code, if we would do this like in the loop, we would basically read up to here, and then it would be like, well, I guess this is the line, right? So we need to have some way, some mechanism of, well, okay, let me back up a little bit as well. What we then would do, because we think this might be a valid new line, right? And then we just read the next chunk into the buffer, then this will be gone from memory, right? So we basically need to find a way to hold on to this data while we're reading out the new data, and then stitch those two together. So, and this is where we could like do some very, extensive well, 2 ways we could do this, right? We could have a line buffer, which is, I don't know, let's say at max it will be 256 characters long, right? Doesn't matter. And 255, whatever. And while we're reading out the start and end of the line, so finding the new line, we could then basically copy this into this buffer and hold on to the line right here. And then later on in our code, we just need to pass around this line buffer. Or the other way we could do this, which might be slightly overkill, would be having another input buffer, essentially double buffering it, and holding 2 to 8 kilobytes of the file in memory at once. Actually, we do not even need to have this a separate buffer, right? We could just say double the space. And then we're just flip-flopping in between those, between reading and writing. Sorry, between reading. So first you read in the first 4 kilobyte chunks. After that you read in the second one. I don't know. I don't know which one I like more. Maybe the line buffer would be like the easiest thing to do. I mean, the absolute easiest way would be read the whole goddamn file into memory at once and just hold on to it. That's also a perfectly valid thing we could do. And maybe I will do that. I have to think about this a little bit more. Reading the whole file at once would be easy. Also, let's think about it. I think the biggest ROM that we can actually, that we have to create, or can create, would be, where is it? Cartridge header. I think I remember this after working on a tool to read out these values, but nope. So 8 megabytes. So let's say the code to create this 8 megabytes would be like 100 meg. And we're compiling a single file at a time anyway, so 100 using 100 meg of memory is nothing on modern systems, right? We have gigabytes available. So maybe I should just YOLO and read the whole file into memory. Just hold on to it. Like this assembler is not supposed to run on like, very old systems anyway with like little chunks of RAM available, so I'll just YOLO it and read the whole thing. Cool. That's it. I really need to take a break though. I'm quite thirsty and hungry and all this kind of stuff.